Hello my friends, welcome again to my video channel. Today we'll start a new old project. I got back a second TR7 which I've repaired in the last weeks or months. We had a TR7 back with bad finals. This is the other TR7. It worked some hours, the operator was very happy with it, or some days I don't know exactly. And suddenly the receiver was deaf, nearly no reception, no output. And the second problem occurred with the passband tuning or passband shift. The sound was the pitch was very high, just as the filter or the passband tuning was shifted away into one direction. Both is not nice. Second problem with the passband tuning occurred after some hours. He told me, I think 3 hours of operation, continuous operation or so. And then the other problem also. The first problem with the deaf receiver and the output, I think, could be with a problem with the pin diodes, the switching diodes. There are switching diodes inside. It's a known problem. And the other one, I think it's a problem with the analog switch. There's an analog switch which switches the tuning voltage for the BFO. But we shouldn't estimate or think about a possible problem. We should measure it. So let's start. The receiver is running. Calibrator is switched on. We can calibrate it. Tune to the calibrator. We can hear it. The audio gain is okay, but the S meter shows nothing. Lower bands okay. The S meter has a little bit of deflection and the signal gets a little bit stronger. That's obvious. That's logic because the calibrator has higher amplitudes at lower frequencies. It's a square wave generator and the harmonics decrease with increasing frequency, but it's much too weak at 3.5 megahertz. It should be S9 plus and we have S3 or so. Odd and even harmonics, no big difference. So we have a deaf receiver and now we look at the transmit. 3.5 megahertz, mode is CW. When I key the transceiver, I can get no output. I see only on the ammeter that the bias current is approximately 1 amp into the PA brick. But irrespective of the setting of this drive knob, of the carrier knob, we have no output and no reaction on the ammeter. So it looks like there is no drive power to the PA brick. I hope so, that the drive power is a problem and not the PA brick itself. I don't need a second PA to be faulty. Okay, let's check the diodes. This is the, let's call it input side of the high pass filter. We have the up converter or down converter. Here we have two switching diodes. They are there to feed in the calibrator signal. And in case there is no calibrator, these diodes are open and then the signal can go through. First we will check these two diodes, whether they are okay or not. Measurement with the diode checker and see what's going on there, whether we have a problem here. These two diodes can be accessed rather easily, one side and the other side. 0.78 and the other one from here to here 0.01. The calibrator is switched off, there is no connection to ground or anywhere else, so it seems that the second diode has a short. Could be the problem. The first diode, which checked bad, is out. It's always better to check diodes out of the circuit, not in the circuit. We don't know which bypasses there are active. It's in the diode voltage measurement. When we connect it, it is 0 and it beeps. difficult. And now I reverse the polarity. Stay, do not run away. Oops. Same. It's conductive in both directions. Well, this diode is definitely bad. I will swap the other diode also. It measured okay, but I think we have to replace both diodes. That is the other diode. In one direction we can measure 0.77, that's okay. And in the other direction it should be infinite. Okay, I cannot get any voltage, it's infinite. So this diode is obviously okay, but as I said, I will swap both diodes. Don't like them to be in place again. Whatever happened, maybe the other diode has a pre-damage. This would be evil to install it. A quick check of the two pin diodes. This is a healthy one. You see, characteristic as it should be. And when I swap it to the bad one, hey, come on, make contact. And we have a short. That's what we have found. The threshold voltage is in the range of some millivolts. So this diode is shorted. And it was necessary to swap it. But when I see the circuit, I don't think that the problem was really caused by these diodes. And the other fault, we have to look for it. Whether it appeared simultaneously, I can't imagine. We have to look for the other fault, what it is. But maybe this faulty pin diode was in there for many years. There are two diodes in series. Okay, so there's a capacitor between the grounds, but maybe this was not very important for the practical operation. I don't know. We will see what the other fault is. The diodes are swapped, but the problem still persists. I have an input signal of 100 microvolt. 100 microvolt, 14.100. This should make S9 plus something. The receiver is still deaf, and when we switch to the calibrator, 75. Same problem, and on 21, 28, in lower bands the signal gets a little bit stronger, but it was as before. No difference. The faulty diode was faulty, of course, but it's not the problem, so we have to search further. The next switching diodes are in the opposite side, in the high pass filter, where we have the PA input and the external antenna jack. So we have here three diodes. In case of reception, these two diodes are conductive. In case of transmit, this diode is conductive. So the power goes to the PA input. In the other case, the external antenna jack goes to the RX path. So we check first in receive mode whether these two diodes are conductive. For this purpose we use a voltmeter. And here we have the input, that is the 13 volt in case of receive. On the other side of the inductor, where it goes to the anode of the first diode, we have 11.6. There's a voltage drop in this inductor here, some volt, but I think this is normal. We are measuring here. This is 11.6, and on the other side of the diode we expect 11 volt, 10.89. This is the anode, 10.89, the same as on the cathode here, 10.89. And on the cathode of this diode we can measure 10.13, and this is the anode, 10.89. So these two diodes are conductive. This voltage goes to the resistor, 10.13, and the other side is nearly 0 volt. There's an inductor to ground. We measure from here to here and to here. So this path, this DC path, is okay with 2 voltage drops as we expect. This diode is the third one, which is here. We have on the cathode a positive voltage, 10.1. It's the same as on the cathode on the other diode. And anode here, sorry, this one, 10.1 and 10.1. And on the anode of this diode we accept nearly 0 volt. That's okay because we are in RX mode, and the 12 volt TX is nearly 0, so this voltage is in reverse direction and this diode is blocked. That's okay. And now we go to TX mode. I fetch the microphone. Power carrier is set to 0. And then we go to the plus of TX. When you go to TX, we have a 13.3 volt. On the anode we have 11.5, and on the cathode we have 10.7 in case of transmit. In case of RX we have the RX voltage from the RX diodes. We are here at this point. So this diode is also okay. So we can say these diodes are switching as they should. No problem. It's difficult to trace an RX signal through a transceiver, but we have the problem that also TX is not working. So I will focus now on the TX, and all modes CW, SSB are not working. So I focus on the mode CW because it's the easiest way to generate a signal, a constant wave with CW. And one of the central points in the transceiver where we have receive and transmit signals come together is the second mixer. Of course the first mixer also, but the second mixer is in the moment better to access. How does it work? Well, we have the first IF. This is 4805 megahertz. In case of receive, we have here 10 volt receive. Then this diode is energized. The signal goes through these two transistors, amplified through this diode, which is also energized via this 10 volt receive path, goes into this ring mixer. Here we have the 53.695 megahertz input, amplified, goes also to the ring mixer, and this is the output, which goes in case of receive through this diode, which is also energized via this 10 volt receive, into the IF board. In case of transmit, we have 10 volt plus here. The signal comes in, the CW signal goes into this ring mixer. This oscillator also comes in, and the output signal, which is 48.05 megahertz, goes through this transistor, is amplified. Here's a small filter. The quality factor is not too high, goes through this diode into the IF in transmit direction. I will check now the transmit path from here to the output. Whether we have first here an input signal, should be 5.645 megahertz CW. Whether we have the oscillator power here and we have the output. This is now the next step to check. By the way, when you see increasing transmit power, I didn't connect a PA termination, a dummy load. It's not problem. The PA supply for the brick is disconnected, so I only energize the transceiver itself with a 13 volt for all oscillators, but not the PA and not the driver stage. This is de-energized because it is not connected, so I can increase the output power without damaging anything. That's important. Well, the first checkpoint is this checkpoint what we have here. This is the input. This is pin 1, CW transmit 0.35 volt peak, 350 millivolt peak input, which goes into the ring mix, and I will measure first whether we have the CW signal here when I key the transceiver and go to full output with this pot. And here we have the screen of the scope, and then we can have a look at it. I will energize it and increase the output power to maximum. Okay, it is not sufficient resolution. We have 10 millivolt times 10 of this probe, so we have 100 millivolt. What is this? It's not a sine wave as expected. There are two signals, not nice. When I reduce the drive power, carrier is set to 0, we still have a signal. Let's measure it. So it's the probe. It's always difficult. We can see we have, without drive power, a signal of 53.695. Not constant. The trigger is not okay. Trigger is not stable. Here we have it, 53.695 with a 200 millivolt peak. And when I increase the drive power as it should be, then we can see there's another signal. This does not look good. The frequency of the oscillator shouldn't go through the ring mixer. It's a little bit too much, which goes through this ring mixer to the input. Again, we are measuring here. This is oscillator 53.695. It goes to the ring mixer, but in the output here, in the middle, in the balanced middle, there should be no output of this frequency which comes in here. But it is. Strange. Now I look at the output of the 48.05 megahertz. What's happening there? The second mixer board is on the extenders with some isolation to prevent shorts. The probe is connected to the output, to the pin where it is stated with 48.05 megahertz. In case of transmit, we should have a peak of 0.6 volt, 600 millivolt peak with the required frequency. The power setting is 0. We have an output 53.695 megahertz. Again, the carrier, or the first, not the carrier, the oscillator is going also through this whole chain, as we have seen. And when I increase the power, you see a second signal comes up. whatever it is not what we want. So I have an assumption that the balanced mixer or any of the nearby components is bad on this board. I will take it out completely and check it, especially the first ring mixer. This would be an explanation for bad reception and also for bad transmit. Such a signal is not what we expect. We expect a strong 48.05 MHz signal and nothing else. I've checked all 4 diodes in the ring mixer, also the series resistors. They are obviously okay. I used also my component tester to look for the characteristic. Yes, there is a problem that there's always a second set of diodes parallel, but the voltages are equal, the threshold voltages, so I do not see any reason if one of these diodes would fail by a short or open circuit, we would see a difference, but all 4 diodes, all 4 resistors are identical. I also checked these pin diodes, they are also okay for switching. I do now another test. The input from the up converter is disconnected, so I can feed in the 48.05 MHz signal. I set the generator a little bit lower, 48.0487, to have an audible tone. The signal strength is approximately 50 microvolt, and we have a signal more than S8. Of course, I cannot align it in the moment because the up converter where the first mixer is done, the first LO operates, is disconnected. So I have a fixed IF fed in with no alignment possibility. Only the passband tuning will work. I can align it. Well, what can we say now? We can say that this path here, from here over the RX to the ring mixer and this diode to the output, 5.645 MHz into the IF, is okay. And I think input value of 50 microvolt for nearly S9 is also okay. This is the input level on the antenna, and there is no gain between here and the antenna. The up converter has input here. This comes from the antenna, goes into the first balanced mixer. This is the VFO or PTO signal or from the synthesizer, and here we have an amplifier. Case of RX mode, the amplifier goes this way into the filter to the mixer we just had, and there is a lot. This input unattenuated, only high pass and low pass filter. There's a loss of gain, of course, of due to the mixer, 10 dB, 20 dB, and this is a gain in this range, so we can assume that the antenna input here has the same level as the output here. No gain but no loss. We see it in case of transmit when we feed in here with 0.6 volt peak and go through this chain here, then the output is also 0.6 volt in case of transmit. So the path is this, mixer, oscillator, and output. 600 millivolt peak here is 600 millivolt peak here. So I assume in case of RX we have the same chain, only in the reverse direction. So the gain is 0 dB. And this is a reasonable value we have. So I'm quite sure now that we can say the problem is not in the second mixer board. But what can we say in a TR7? Everything is possible. but now I will focus on the up converter. Here we have the so-called up converter. This converter converts the incoming signal 0 to 30 megahertz from the high pass filter, where we check the diodes, converts it up to 48.05 megahertz is the output, which goes to the second mixer. And here on this side we have the infeed of the VFO frequency or VCO, which is always 48.05 megahertz above the receive frequency here. So we have a difference frequency of the 48.05, which is the first IF. The schematic is rather simple. First checkpoint is this transistor, which is an amplifier in both directions. Could be the problem. We have an RX and TX problem. So let's check the bias setting first. The transistor, this one pin should have 9.95. Where is it? Here is it. Oops, 9.9 something. That's okay. And the source should have 1.3. We have 0.93. Okay, it's a little bit low, but I don't think we have a problem. You hear when I touch it, we have an increase in the noise. So I'm quite sure that the transistor is okay and operates. Next check will be the switching diodes. We have here 4 switching diodes. 401 and 404 is for receive path. The received mixed signal comes in here, goes to the source, comes out in the drain, and goes via this diode to the output filter to the second mixer. So we check these two, whether they are conductive. The 401 is this here. On one side we have 9.9. Yes, it's 10 volt minus a voltage drop over control resistor, and 9.1. That's okay. 0.8 volt voltage drop. We will use later a signal generator. And now we have the 404, and the 404 is where? It is CR404. It should be this one. (9.1) and 9.9. So these two diodes are okay, they are working, and I'm sure they are conductive. So let's use a signal generator to feed in a signal and see what happens. But first we will check the LO frequency from the first LO. It should be a peak voltage of 0.9 volt in the input. This is the input. We have 7 megahertz, 0. So we have 48.05 plus 7 is 55.05 megahertz. That's okay. When I start tuning it, 100 kilohertz up. (55.1) 15. Okay. So this frequency is okay, and the amplitude is also okay. We have 500 millivolt per peak. So we have 1.2, 1.5 instead of 0.9. We have a little bit more than specified. A problem could be the amplifier, so I check the input at the double balanced mixer. It is pin 8. Pin 8 is this one. Oops. A little bit more. So I can say that this amplifier chain is okay up to the input of the double balanced mixer. I feed in here a signal in the input, which is this connection from the high pass filter, this point, The connector is unplugged from the high pass filter. Signal generator is directly connected. Set to 50 microvolt and we have nearly no reception. This is not good. 50 microvolt should be approximately S9 or so, or S8. But here we have nearly 0. So there is something wrong. This goes to the mixer. This signal is okay. Now I will check when I feed in a signal here what's happening, or maybe it could be easier to transmit and look what's going in here and coming out here, whether the double balanced mixer, whether this double balanced mixer has a problem or not. I think I will make CW mode and measure the output signal. Next checkpoint is this point here. It's the output of the chain filter, amplifier, switching diode on R413. That's the input of the double balanced mixer in case of transmit. I'm connected here. We can see here also the LO frequency. I go down to 0. It's 55050. And when I go to transmit, and when I increase the drive level, the carrier, we see there is a second signal. So the first assumption is we have here amplification of the signal, but we have here feedback from the double balanced mixer also, as we had with the other from the local oscillator here. Next chain is 0.4 and 3. It's the output to see whether there's something coming out. 1, 2, 3, 4. Again, nearly impossible. Oh. Go back to 10 millivolts. That was the original sensitivity. There is nearly an output signal. Only the carrier, very strong. We are measuring here. Now I go behind this low pass filter. It's a low pass filter. And measure this point here where it goes to the high pass filter, which is this connection. We connect the scope to here. This cardboard prevents only shorts. So the frequency of 55 megahertz what we had is gone. I'm going to go to transmit. No output signal. In case of transmit, we should have here 0.6 volt CW transmit. Nothing. And this is unloaded. The filter, high pass filter, is not connected, so the voltage should be a little bit more. But what we have here is we have 10 millivolt, 100 millivolt per division. So we should have here a signal over several ticks here. We have nothing, even with full carrier setting. So this output here supplies no voltage to this. The output of the mixer gives no output to the connector here. Here we had a little bit of signal, but here we don't have a signal. Maybe we have an interruption here in this line. I do now a reverse check and feed in an RX signal here, not here. I will fix first. I will connect the signal generator to here and then to here. This will be the next step. I feed in a signal of 7010 kilohertz on exactly 7000 there's a small birdie inside 7010. We have a very weak signal as we had before, and now I will connect the signal generator to the input of the mixer. I have to look for a ground connection. One moment. Now I tap the pin 3 and 4. Again a very weak signal. Same as here. So I can say the low pass filter is most probably okay. Do we have a problem with a double balanced mixer? Could be. Some final checks of the ring mixer, balanced ring mixer, whether it is really bad. That's the input of the LO. The LO frequency is 62.05. This is 14 megahertz. The set frequency band plus 48.05. And then it's 62.05 megahertz. The level peak is 185 millivolt times 10 for the probe. It's 1.85 volt. I note it simply on my volt peak at the input. I don't have a data sheet for this balanced modulator ring mixer for the old CM stroke 1HF. Couldn't find it in the net. Not so important, but the isolation between the LO port and the RF port should be 40 or 50 dB, and you see it is much less. We have 0.4 volt in the RF. This is approximately 4 times or a quarter of the voltage of the LO here on this side. This is only an attenuation of quarter voltage. It's a 1 by 16. It's 13 or 14 dB. 13-14 dB and not 4T as we could expect. And also for the IF connection here, we also have a very bad isolation. And again, we have no output signal here. As we have measured, we only have the LO signal. So I'm very sure to say that this balanced ring mixer is bad and I have to replace it. In one of the Drake forums or another paper, I've read that the SRA 3MH could be a substitution. The plus only means that it is compliant with the regulation regarding chemical industry and so on. ROHS compliant. Okay, not important for me. This type has a conversion loss of 4.77 in the mid band. When we go to the conversion loss, for example, RF 35 megahertz oscillator 65, we have 5.1 dB loss. This mix is at the moment not available on the market. I have to ask for offers when I buy one or two. You can imagine what the response will be. So I will take another one. There are two on the market. SBL 1. This one, it has a little bit more conversion loss, 5.6. The other one had 4.77. Okay, it is 0.9 dB more. And here on 32, 62, we have 5.6 dB. And the other had 5.1 dB. This is a low power level 7 frequency mixer. The LO power should be plus 7 dBm. I've calculated the input voltage on the pin which I measured with 1.8 volt peak. That's 0.65 RMS, that's 8.5 milliwatt or 9.3 dBm. This is a little bit more than the 7 dBm, but the RF power can be up to 50 milliwatt. This means, of course, the level for best linearity, and I am a little bit above it. So I think the SPL1 could be a solution. Terminally, it is not overloaded, so we can use it. There's a version of the SPL1. This is the SPL1 MH. It is a level 13. Also has RF power 50 milliwatt. Conversion loss is 5.7. And the other one, SPL1, had 5.6. And at frequency 47 and 77 we have 5.6 dB loss. And in the similar frequency range we also have 5.6 dB. So these two mixers are identical, SPL1 and SPL1 MH. Only the MH version has a low power of 13 dBm, which is required. It is specified 1 to 500 megahertz. We can it operate down to TC because the diagram in the TR7 is that the receive frequency is fed in the IF chain DC to 500 megahertz. Here we have the RF from the antenna fed in, or that's the output of the transmit path. And the LO is the LO and the RF is the other frequency, which is coming from the second mixer. So we have an IF of DC to 500, and that's what we can see in the electrical schematic, which is this here. This is the IF output, and this is DC coupled to the ring, so we can here feed in DC and modulate these diodes also with DC. Here we have the LO input, and here we have the out and inputs regarding RX or TX. So here is the antenna connection or the output to the PA driver, and this is down to DC. That is a difference in the schematic. It is not truly as here. The RF is not connected to this input, it is connected to this input. But mixer is mixer, doesn't matter. Well, my decision is I will order this one, SPL1MH. It is available on the market, and it is only a question of some days. It's not so expensive, can be paid. There's nothing cheap today. Everything costs its money. So we can say for our use it's 0 to 500 megahertz, or DC path. IF is DC to 500, and LO and RF. Sorry. And LO and RF is 1 to 500. That's okay. And here's the DC to 500. Well, that's the solution. I will swap the mixer. And then I'm sure, what is sure? 99%? Yes. I keep 1% as a backdoor to disappear behind the backdoor when it is not correct, when this mixer is not a problem, but I'm sure at 99%, and 1% is safety belt for me. The unsoldering of the ring mixer is not so easy, because there are two holes. And there is the case of the ring mixer soldered to this shielding, and to get access to this hole it's necessary to unsolder this contact, same contact as this one, but it is here, and we have to take out this contact, and we can unsolder it, bend it a little bit up, unsolder this side, and then there are 2 or 3, we have to look for it, contacts through on the side, through the board, and then of course the shielding here also has to be unsoldered, and then it should be possible to flip out. Here is another hole. I have to unsolder this one also. Now the shielding is off. We had indeed 3 holes, 1 to 3 holes, and the was soldered, okay, not on this side here, but on this side and on this side the shielding was soldered to the case of the mixer. I think it's not necessary. Maybe it's a different type where the case is not grounded or so, I'm not sure. What is it? SM759 VAR L company, SM759. I look in the net whether I find some data about this mixer. Anyhow, it has to go. And the new mixer I don't connect to all 3 sides, maybe only on one side, sufficient, because the case is grounded and will be connected to the chassis, to the PCB on this side here, and also here. Okay, that's the first success. And now we can see the reason for this strange ground connection of the case. None of these pins here is connected to the case of the mixer. So the case is isolated from all pins. So it is indeed necessary to have a separate ground for the case. And therefore it was soldered here and here, and obviously it was intended to have a solder connection here on this side, which wasn't there. That's the reason for this strange connection. The new mixer I've ordered, they have I think 2 or 3 pins connected directly to the case. I will have a look at the 3, 4, 5, 6, 7. Here we have it. Ground 2, 5, 6, 7. There are 4 pins connected to the case. 3 and 4 is isolated for the IF. 1 and 8 for LO and RF in. The other ones are connected directly to the case. Sorry. 8, 1 and 3, 4 is isolated. 2, 5, 6, 7 is ground. So I do not need this method of grounding, as we see here. Now we can replace it and make it a little bit easier when we reconnect it. Bend it back and remove the solder on both sides. That's a little bit easier. Okay. I could clean the surface of this mixer. Is it a dash, also very L company, SM759. Never heard about this type. I will look into the net. On the other hand, it's not so important to have the data, it has to go. Would be nice. Let's see what I find. And while I'm waiting for the new balanced ring mixer, I decided, just to satisfy my curiosity, to open the old one, the bad one, which I assume it is bad, 99% or so. Cut around with a small saw, then I can take it out. Here we have some foam or similar. No, it is not foam, it's the plastic. No, it's also not plastic. Can't say what it is. Feels like plaster or so. Seems as this material, I think it's plaster or similar, can be dissolved by simple water, and then I can easily scratch it out with this dentist tool. It's a little bit of tricky work, but it can be done. It's a question of some patience. Drink a beer and continue the work slowly, not to damage anything, and then we will have a result. Here's the inside view of the mixer. Here we have the diode ring. These are 4 diodes. A little bit of strange appearance. Here we have the 2 cores, ferrite cores. Each has 4 turns. We count here 3, and 1 goes through it. This is a second one. 1 through it is 1 turn, and if we come back, it's the second, third, and 4th. So we have the totally 4 turns. Outside we calculate 3, but inside we have 4. These 2 transformers are identical. I assume also identical material, ferrite material. Why should it be different? Here we have the input, 7, 8. 7 is not grounded. This and this is 5 and 6. This is fed out separately. We have no connection. 5 and 6 is open. Each has a pin and can be grounded externally. Same as 4 and 3. These 2 and 1 and 2. 2 is grounded. The pin looks isolated from outside, but indeed internally it is bent back by 90 degrees, 180 degrees, and it is grounded. So we have here the pin, yes, I call it pin 2, could also be pin 7. It's the same, it depends whether it is arranged 180 degrees inverse or not. And this is a diode ring. We have here 2 connections, this and this, from this turn. This is corresponding to this, and the other 2 of the diode rings connected here and here, and this is this and this. In our application in the TR7, 4 and 3 is connected together on the board and fed to the 30 megahertz low pass, as we have seen. 5 and 6 is grounded. So we have indeed this configuration. And then I don't know, I have to look into the schematic whether we have 2 is grounded or 7 is grounded. But in general we have this one for the diode ring. And now I will check where the fault is. I'm not sure. The transformers itself look okay. Also the connections, the solder connections here, they are not bad. Also these 2 here look good, and these 2. Maybe one of the diodes here is bad or not. So I will separately measure it. Well, the new one, which I've ordered, also looks, I'm sure, similar inside. Whether we have a diode ring of this style or different style, I don't know. The brown one is only plastic. It's an isolation. It's just for support, but it has no electrical influence. This diode ring is out of the mixer. It was only glued a little bit on the case here on the bottom with a drop of glue. I do a diode voltage check. You see the voltage of the diode indication and the clockwise rotation, first the minus, then the plus pole. Minus, I glued it on the paper, otherwise it would flip away. 0.14. The next one has 0.09. Next one has, okay, this looks like a short. And the next one also has a short. Obviously 2 of them has a short. I swap the sequence of plus and minus. Okay. When I reverse the polarity of the healthy ones in one direction, (0.14), and when I reverse it, same 0.11, because two of them are shorted, so we have two diodes which are okay and two are shorted, so I measure always the same voltage, because these two here are anti-parallel when the other two are shorted. I show it in the diagram what I mean. That's what we have. Two diodes are okay and the other two are shorted. When I measure plus and minus from here, I measure this voltage, and when I measure minus and plus from here, I measure this voltage here, because the two other are shorted. So we have this configuration. I assume two of them are shorted. Due to any reason, I don't know what happened, but that's obviously the problem of this ring mixer. The new mixer has arrived, SBL1MH. Pin 2 is this one, as described in the datasheet. Under the MCL node there is pin 2. 3 and 4 is the input, which has to be connected together externally. It is stated in the datasheet, IF 3 and 4. Stated also here has to be connected externally. That is given here, 3 and 4. When we look at the bottom side, we see here these two pins are connected via this trace and connected to the ferrite bead, which is also shown in the here in the schematic. That's the ferrite bead. So we can insert this mixer in this way, solder it, and look whether it works. When soldering the ground pins here on the ground plane, use a big iron, not a small one. This is good to have an iron with some power, to have a short time for soldering, to be ready within some seconds. This big one is okay. That's it. And before I reinstall the shield and connect the second braid, it's the second braid here. The coax cable here has one braid which is connected to the ground here, but this is obviously a second one which is slipped over the coax cable for better shielding. That's a good idea because we have here the RX path also, so it's good to have a second braid. But for a test, it's not necessary. I will plug it in this way and see now if the receiver works. Look what we have. Full reception of the calibrator. It's the odd harmonic 25, 7, 14, 21, 28. And the even one is a little bit weaker. Then the odd one, that's normal. Full reception on all bands. And now let's check, first step, the PA. Without full power, I only want to check whether there is an output. I don't want to operate it with full output when we have this open configuration here, but somewhat output would be okay to see how the PA behaves. And now the test of the output, 7 MHz in mode CW. When I key the transceiver, of course with connected dummy load, I can increase the output power, 100 watt and more. Let's go to 28. Nearly also 28. What does the... Okay, ALC reacts, but also we have output. So there is no damaged PA. As I said, some footages before, I don't need a second TR7 with killed PA transistors. So obviously this PA here is okay, this brick. No further action needed. Next step is to finalize this first mixer or the up converter or down converter install the shield, bring it back into the casing, and then we have a second problem. It's the PBT, which sometimes now it works, but the owner said there is still a problem that the PBT, the passband tuning, sometimes makes trouble after some hours of operation. But first I will close the case and make this finalized. The problem in the up converter with the double balanced mixer, the ring mixer, now is solved. We have full receive and transmit as it was before when I sent this transceiver first to the owner. But there is still another topic pending. It's the passband tuning, or better said passband shift. The owner told me that after some hours of operation there is a problem. It sounds like suddenly the frequency, the IF filter shifts up and the pitch gets very high, as in RTTY tuning. Okay, the board under suspect is already on the extenders, but this will be part of the next video. So stay healthy, stay tuned, see you on this channel.